Hello everyone, this is Dr. Mahantesh. I am a faculty in the Department of ECE, PES Institute of Technology and Management, Shivamogga, India. Today I would like to present my paper, Optimizing NeRF, a comprehensive review of the impact of different optimizers on neural radiance fields. Let's continue the topic. The contents of the presentations are as given below. Let's start with introduction to NeRF and what are the importance of NeRF optimizers. Then next we will discuss about key optimizers for NeRF. There are 4 optimizers that we are comparing the performance of different analyzers. Then what is the method behind this NeRF that we will be discussing, and dataset and performance metrics, performance comparison. At the end we will try to conclude which optimizer is very much useful for a given application. What is NeRF? Neural Radiance Field is a deep learning model that represents 3D scenes from 2D images. It produces photorealistic images from minimal input images. The key features include continuous volumetric representation, photorealistic rendering of complex scenes, and efficient training with large datasets. So it's not only from 3D scenes from 2D images, we can also, there are references in our paper where they are projecting 5D image from 3D scenes, which is quite possible and which improves the quality of the rendering of complex scenes. So let's go ahead and check what are the different things. Why we need optimizers in NeRF. There is enough mathematical background to it, but if you would like to see the role of optimizers in NeRF model is to minimize the discrepancies between predictions and actual data. The choice of optimizer is significantly affects the final reconstruction quality. Effective optimizers lead to faster training and improved model performance. So these are the things that we observed during our work. We felt optimizers are essential part of NeRF now, and there are other things that are also available, and I'll be discussing at the end of the presentation. The method includes what exactly it does. Normally it's a machine learning thing. The training process will take the test data, which involves initializing the parameters, then feed forward pass, and then calculating the losses, and then back propagation. Then we'll go back and check and updating the parameters using optimizers. This is a typical machine learning step, but a bit of modification based on the optimizers and machine learning technique. The goal is to minimize the loss function, which measures the difference between original and rendered image. So this is the final goal. Okay, let's go ahead and check what are the, if I try to get the data set, suppose if the data sets are maybe both synthetic and real world images. In our paper we clearly mentioned even these things can be toys or 3D images generated from computer. These things can be considered as a data set and can be included in NeRF. to make it more realistic. The performance of this NeRF is based mainly measured using PSNR, peak signal to noise ratio, and the quality of the rendered image to the original image. If it is higher PSNR, it is better quality. If it is lower PSNR, it is lower quality. So this is the performance metric now. Typical the toys example what we have taken, and these data sets are available, and different examples may also be taken. In this we are just taking this as an example. There are different optimizers, key optimizers for NeRF. One is ADAM, that is adaptive moment estimation, which combines concepts from momentum and RMSProp. Second one is AdamW, that is Adam with weight decay regularization, which is considered the best of high quality NeRF models, which you can see it in the next upcoming slides, where PSNR is very much good. The third one is RMSProp, which uses moving average of squared gradients for learning rate adaptation, which is efficient on large data sets. So if you have large data set, you go for RMSProp. Then there is something called as Adagrad, which is adaptive learning rates based on past gradients, which is suitable for data sets with many parameters. Okay, now we have different NeRF optimizers. Each one has got its own advantages and drawbacks. But when it comes to performance, you should be able to see which is good. But also you should be able to see what are the type of data sets we have. Suppose if the data set is too large, we should go for RMSProp. If data set is having many parameters, then we should go for Adagrad. Then if you want high performance, simply we should go for AdamW. These are the different things that we will be discussing. We would like to take 1000 iterations as a reference, and showing the PSNR of the result. Okay, the adaptive moment estimation, the Adam combines concept of moment as we already discussed. These are the results of Adam, which is having around 22 plus PSNR, which is good. Then comes AdamW, which is having weight decay regularization, and these are the results, which is giving bit more efficient result compared to Adam. Then comes RMSProp, which uses moving average of squared gradients for learning rate adaptation, which is already discussed. If you have too many data sets, it is more useful. The results also showing it is gradually going compared to the previous one. It is quite linear in terms of PSNR, and after that we have Adagrad, where the PSNR is quite it has got its own advantage, as I already discussed. It's okay if you have different things, but the PSNR is very low compared to the other one. So comparing all four different NeRF optimizers, we have a comparison of the PSNR values in a single table. But if I would like to conclude with comparison of all these, Adam consistently improves PSNR. We could able to see the blue one, which is consistently improves. making it effective for small data sets. So as I already discussed, if you have small data sets, Adam is good because it's quickly improving. And also within a limited training time, Adam is very good. AdamW emerges as superior in our context. So this is also good compared to Adam. AdamW is better. RMSProp performs well on large data sets, but PSNR is a bit low. While Adagrad, though adaptive, shows slower convergence in this study. So this is fine, but it's slow. It is slow. There is no question about it. So it is already indicating, but it's okay. These are the things that we tabulated in the performance comparison, and this image is a bit small, so I would like to go back to our paper and show that table. Okay. So if I see it in a larger manner, the Adam demonstrates a clear and consistent upward performance trajectory during the training, efficiently improves model performance. So initial PSNR and the peak PSNRs are about 7.8 to 23.12 respectively. The notable features are momentum based with adjustable learning rate, effective for rapid quality enhancement in shorter training intervals, which is well suited for limited training time and smaller data sets. So it has its own advantage. When it comes to AdamW, the relative performance must be assessed through empirical experimentation. Significantly improves PSNR from 7.77 to 23, which is quite notable. Effective optimization, particularly when applied to a specific data set and model. Then the suitability of this, we observed it as demonstrates superiority in certain context. Okay, in some applications, it is very good. RMSProp, which displays a clear inclination for performance improvement, and with a modest increase from say 7.85 to 20, it's okay, but adaptive learning rates, okay, you can see that it may fall short compared to Adam, but performs better with substantial data sets. If the data set is too large, then RMSProp is good. Adagrad fails to produce with the current context, if I say despite of gradual increase from 8 point to 9.5, adaptive learning rate based on the gradient magnitude best suited for large data sets. Okay, this is but if I compare with the first three, it is not so well performing, but because as I already told, it may suffer from slow convergence. So this is about comparison. When it comes to the remaining part, that is conclusion, the best optimizer for NeRF varies based on the dataset size and complexity. Adam is generally effective and AdamW excels in specific context. RMSProp is efficient on large datasets, and Adagrad is suitable for extensive datasets with prolonged training. Future research should explore hybrid and advanced optimization methods for NeRF. This is all about the presentation, formal presentation, but I would like to extend it. If one of the prominent work and we are impressed with is the reference number 13. Okay, Milden Hall, Srinivasan, Tansik, Baran, and Ramamurthy, and R. Neg, which did very good work, and we are very much impressed with. Without discussing that, I think this presentation would be incomplete. So let's go to that reference. What they did, we can able to check. This is the their website, and what they did is very fantastic with respect to the NeRF. So this they presented, and if you see their work, okay, they try to do it from you can see that 2D 3D, and you can able to see that there are 5 parameters x, y, z and theta phi. From that they are trying to generate phi, which is very nice work. So the spatial locations, what they are trying to do is single from this fully connected non-convolutional deep network, whose input is 5D coordinate. 5D coordinate includes x, y, z, which are 3 coordinates, and theta phi from the other coordinate systems. From that they are trying to generate volume density and view dependent radiance at the spatial location, which is very good. The results of their work are presented in the form of videos, which are very much impressive. We can able to see that this is the final output what they got, which is fantastic, and which they the image is given, recorded video is given as input. From the recorded video they could able to get these outputs, which is very fascinating. You can also able to see the different angle version of the outputs. The applications are very fascinating what they have mentioned. So in the particular video they mentioned what are the applications and all. So this is very nice work, and thanks for motivating us. And with this I would like to end the presentation. So our paper will be appearing soon in Bulletin of Electrical Engineering and Informatics. So we did very good work, and thanks for BEEI and editor and other team. Thank you very much.